Hello and welcome to this short video where I'd like to share with you an interesting formula that I came across while making cookies for the Singal and Tamil New Year. So while I was making cookies, I started considering the sums from r equals 0 up to infinity of r to some power k divided by r factorial. And while considering these, I realized that I kept getting integer multiples of e. When I considered the sum from r equals 0 to infinity of r divided by r factorial, I got e. When I considered r equals 0 up to infinity of r squared divided by r factorial, I got 2e. And so I thought, maybe there's a connection here. And after thinking about it, I realized that the following is true. If you have the sum from r equals 0 up to infinity of a sub 0 plus a sub 1 r to the 1 plus a sub 2 r squared plus a sub 3 r cubed and so on until a sub n r to the power of n, where n is some positive integer and all of these coefficients a0, a1, a2 and so on are all integers, and all of that is divided by r factorial for each term, then the result you get is an integer multiple of e. So here we have e and here we have k, which is some form of integer. So I just realized this and I realized it's something significant. However, of course, I wasn't the first to discover this. In this day and age, it's very difficult for you to discover something originally. This formula is called Dubinsky's formula and was found by G. Dubinsky and published in 1877 by him. What we're going to be doing in this video first off is to prove that this is true, and afterwards we're going to take a look at the coefficients k that appear in front of e for different powers of r, and we're going to consider r to the power of 1 divided by r factorial sum from 0 to infinity. We're going to consider r to the power of 2, r to the power of 3, r to the power of 4 divided by r factorial and so on. And then we're going to see a pattern that arises from that, and we're going to see a method to generate the coefficients of e in each of those numbers. So first off, let's discuss how we can prove this thing. To do that, we're first going to start with the Maclaurin series for e to the power of x. If you're interested in that, click this video on the top right here. But let's just go ahead directly and write down that Maclaurin series. In that video and previously, we found that e to the power of x equal to 1 over 0 factorial plus x over 1 factorial plus x squared over 2 factorial plus and so on and so forth. X cubed over 3 factorial, x to the power of 4 over 4 factorial and so on. If we do e to the power of 1 here, as in we substitute e to the power of x with e to the power of 1, substituting x equals 1, we get that e to the power of 1 or e is equal to 1 divided by 0 factorial plus 1 divided by 1 factorial plus, and then 1 squared is still going to be 1, so it's 1 divided by 2 factorial plus 1 divided by 3 factorial and so on. So here we can see that e is equal to the sum of all the 1 divided by x factorials. So in this case, instead of x, we'll use r and say that e is equal to the sum from r equals 0 up to infinity of 1 divided by r factorial. This is going to be our starting point from which we're going to build up all of the sums. Now at this point, in order to progress, what we're going to do is to next use mathematical induction. If you don't know what mathematical induction is, click this video on the top right here. Mathematical induction is going to allow us to prove that the sum from r equals 0 up to infinity of r to the power of n divided by r factorial is equal to k times e, where k is some element of the integers, provided that n is some element of the positive integers inclusive of 0. Now, in order to prove this using mathematical induction, we're going to need two things. We're going to need a base case, and then, assuming something is true, we're going to need an inductive step that relates a certain value being true for one certain value of, in this case, n, to the next value of n. So for our purposes, first off, for the base case, we can consider n equals 0, since that's the lowest value of n in the set of positive integers inclusive of 0. If we substitute that into here, we can see what we need to find is the sum from r equals 0 up to infinity of r to the power of 0 divided by r factorial. But r to the power of 0 is just 1. So we have 1 to the power of 0, r to the power of 0, which is 1, divided by r factorial, and we need to sum that from r equals 0 up to infinity. So we have the sum of r equals 0 up to infinity of 1 divided by r factorial, which is exactly what we have up here. Therefore, we have already established our base case. We can label this as 1, call it our base case, and now what we need to do is to establish our inductive step. So the inductive step I would like is an inductive step that says if it's true for n, then it's going to be true for the next value, which is n plus 1. Now, in order to do this, as it turns out, we actually need it to be true for all the values from n starting from 0, 1, 2 and so on all the way up to n, but that's not a problem since we are building up gradually. We'll go from n equals 0, and then if it's true for n equals 0, we'll prove for n equals 1, and then if it's true for n equals 0 and 1, then we can prove for n equals 2 and so on. But since we've already proven for n equals 1 by the time we're going for n equals 2, it's not a problem. We can use those two results to build to the next one. So having the requirement that we need this to be true for all of the numbers from 0 up to that current value of n, in order for the next value to be true, is not a problem. We can work with it. So now let's assume that it's true. Let's assume that the sum from r equals 0 up to infinity of r to the power of p divided by r factorial is equal to sum k times e for all p's starting from 0 up to n. So we'll say for all p which are elements of the set starting from 0 going to 1, 2 and all the way up to n. So we're going to assume that this is true. And now what we're going to do is to assume that is true and then consider the next value after this, which would be the sum from r equals 0 up to infinity of r to the power of the next value after the last value we're going to consider, which is going to be n plus 1. So we're going to then consider the sum from r equals 0 up to infinity of r to the next power, or r to the power of n plus 1 divided by r factorial. Now considering this thing, first off, if we just write out a bunch of the terms, the first term here is going to be 0 to the power of n plus 1 divided by 0 factorial. The next term is going to be 1 to the power of n plus 1 divided by 1 factorial. The next one is going to be 2 to the power of n plus 1 divided by 2 factorial and so on. Now we can see the very first term is 0 to the power of n plus 1 divided by 0 factorial, which is going to be 0. And due to that, we do not even need to consider the r equals 0 term, because considering the r equals 0 term and not considering the r equals 0 term are the same. We might as well just start the sum from r equals 1 and go upward. So therefore, the sum from r equals 0 to infinity of r to the power of n plus 1 divided by r factorial is the same as the sum from r equals 0 up to infinity of r to the power of n plus 1 divided by r factorial. Sorry, I actually wrote the exact same thing again. It's supposed to be r equals 1 to infinity of r to the power of n plus 1 divided by r factorial. So these two sums are exactly the same because the first term does not contribute anything in the very first sum. Now that we have this, what we're going to do next is to consider r to the power of n plus 1 and r factorial and realize that r factorial actually has an r inside of it. And the reason for that is that r factorial, or the factorial function in general you could consider, has the property that any factorial is equal to that number multiplied by the previous factorial. So in this case, r minus 1 factorial. So using this identity here, we can see that this r factorial on the denominator could actually be written as r times r minus 1 factorial. So therefore we can write that this is equal to r equals 1 up to infinity of r to the power of n plus 1 divided by r times r minus 1 factorial. Now we can see we have an r on the denominator, and additionally we also have an r on the numerator. We can see we have more than one r, we have n plus 1 total r's, which means if we cancel out this r for one of the r's, we'll be left with n total r's on top, as in r to the power of n on top. Meaning that our sum is now the sum from r equals 1 up to infinity of r to the power of n divided by r minus 1 factorial. R minus 1 factorial. And now at this point we can see that all of the terms here, if we just write a couple of them down, are going to be, first off, for r equals 1 is going to be 1 to the power of n divided by 0 factorial. The next term is going to be 2 to the power of n divided by 1 factorial. The next term is going to be 3 to the power of n divided by 2 factorial, and so on and so forth. We can see that we could instead start counting from r equals 0 up to infinity, and instead of having r here, we could have r plus 1, because 0 plus 1 would be equal to 1, 1 plus 1 would be equal to 2, 2 plus 1 would be equal to 3, and so on. And on the denominator, we could just have r factorial, since when r is equal to 0, that would be 0 factorial, and then we'd have 1 factorial, 2 factorial, and so on. So therefore, this sum is the same as the sum sigma r equals 0 up to infinity of r plus 1 to the power of n divided by r factorial. The same exact thing, because if you consider substituting the values of r, both of these sums, this sum and this sum, give the same exact terms. Now, if we consider this sum, we can see that on top we have an expansion that we need to expand. This expansion can be expanded using the binomial expansion. If you want to know about the binomial expansion, click this video on the top right here. So using the binomial expansion, if we substitute into here, we can see that what we get is equal to the sum from r equals 0 up to infinity of all the terms which are of the form on the top. We have the binomial expansion of this thing, which is going to be the sum from, we can't use r here since r is already used as the counting variable for this sum. So we'll use L or something. L equals 0 up to n of n choose L of r to the power of L times 1 to the power of n minus L. Now in this case, 1 to the power of n minus L is always going to be 1. So we can actually cancel it out, since multiplying by 1 is always going to give the same exact thing. So we can remove it, in which case we get this sum divided by r factorial for each of the individual terms, which are then added together from r equals 0 up to infinity. So now we can see we have this. If we go to the next page and start writing this sum down, we can see this sum is going to be equal to the sum from r equals 0 up to infinity of each of these terms in this sum, which is going to be all the terms from L equals 0 up to n of n choose L r to the L. Now if we start writing them down, this is going to be first off L equals 0, which is going to be n choose 0 times r to the power of 0, which is going to be 1, and the next term is going to be n choose 1 times r to the power of 1 plus n choose 2 r to the power of 2, and so on until the last term, which is going to be n choose n times r to the power of n. And then that's all going to be divided by r factorial, which we can split into individual sums, which are all going to be of the form the sum from r equals 0 up to infinity of some integer, which is going to be a choose function value, times some power of r divided by r factorial. If we do that, we can see that the sums we get are first off the sum from r equals 0 up to infinity of the first term, which is n choose 0 r to the 0 divided by r factorial, plus then the second term, which is going to be sum from r equals 0 up to infinity of n choose 1 r to the 1 divided by r factorial, and the next term after that is going to be sum from r equals 0 up to infinity of n choose 2 times r squared divided by r factorial, and this is going to go on until the last term, which is going to be sum from r equals 0 up to infinity of n choose n, which is going to be 1 times r to the power of n divided by r factorial. Now if we take all of these coefficients of n choose something out of here, we can see that what we get is n choose 0 times the sum from r equals 0 up to infinity of 1 divided by r factorial plus n choose 1 times the sum from r equals 0 up to infinity of r divided by r factorial plus n choose 2 times the sum from r equals 0 up to infinity of r squared divided by r factorial, and so on until the last term, which is going to be n choose n, which is 1, but we'll just leave it as n choose n times the sum from r equals 0 up to infinity of r to the power of n divided by r factorial. So this is what we get. Now notice here, all of these terms n choose 0, n choose 1, n choose 2 up to n choose n are all integers. So I'm multiplying a bunch of these sums here by integers. Now consider the sum parts. The sum parts are first of the sum from r equals 0 to infinity of r to the power of 0 divided by r factorial, and then r to the power of 1 divided by r factorial, r to the power of 2 divided by r factorial, all the way up to r to the power of n divided by r factorial. Now recall our assumption at the beginning. Our assumption is at the beginning was that we are to assume for all p which are elements of the set from 0, 1, 2, 3 all the way up to n, that the sum from r equals 0 up to infinity of r to that power divided by r factorial is an integer multiple of e. So from that assumption, all of these sums over here are integer multiples of e. This is an integer multiple of e, this is an integer multiple of e, this is an integer multiple of e, all the way up until this final sum, which is also an integer multiple of e. So if all of these are integer multiples of e, and at each of these terms we are then multiplying them by some other integer, an integer multiplied by integer is going to remain an integer, meaning that this thing right here is some integer multiplied by an integer multiple of e, which means that this is also some integer multiple of e. The next term after that is also going to be again by the same principle, another integer multiple of e. This is going to be an integer, this is going to be an integer multiple of e. Multiplying them together, you get an integer multiple of e. Then the next term after that is again going to be an integer multiple of e. The term after that is going to be an integer multiple of e. And finally, the last term here is also going to be an integer multiple of e. Now, when you add a bunch of integer multiples of e together, you're going to get another integer times e. Since, if you add any number of integers together, you're still going to be remaining within the set of integers. So due to this, the total sum here is also going to be an integer multiple of e, which I'm representing by k. Remember, k is just some random k, which is an element of the integers. So given this, we can see how if we take all of these sums and we add them all together, we're going to still get an integer multiple of e. Now, this is not actually the final step in mathematical induction. Usually in mathematical induction, you would want to make a formal statement regarding the results that you found above to actually prove it. So let's just do that right now. The formal statement we're going to put in this case is going to be something like, hence, we'll say, since the above, because I don't really want to write the whole thing again, since the above was shown true for n equals 0, which was our base case, and when assumed true, well, in this case what we assumed true was that for all p, which were elements of the set of numbers starting from 0, 1, 2, all the way up to n, was found true for the next value, found true for, in this case, n plus 1, we can say that if it's true for all the values from 0 up to a certain value n, it's true for the next number. So then, since it's true for 0 implies true for 1, which then implies, actually we would write something like this, because you need it to be true for 0 and 1 to prove it true for 2. So then it's true for 2. And then if it's true for 2, then it's true for 3, since we've proven that it's true for 0, 1, and 2, and then so on and so forth. So you would say that as a final statement, it is found true, the result is true for all the set of numbers that we can cover by using this method. So we can start from 0, and then using 0 we can prove 1, using 0 and 1 we can prove 2, using 0, 1 and 2 we can prove 3, using 0, 1, 2, 3 and 4, so the 3 we can prove 4, using 0, 1, 2, 3 and 4 we can prove 5, and so on. So therefore it's true for the set of numbers that we are generating by that, which is 0, 1, 2, 3 and so on. So that is the set of positive integers inclusive of 0. So it's true for n, which is an element of the positive integers inclusive of 0. So it's true for all of these numbers, for n equals 0, n equals 1, n equals 2, and so on. So now with this, what we've proven is that up here, if you have the sum from r equals 0 up to infinity of r to the power of n divided by r factorial, it is going to be equal to an integer multiple of k for all the values of n which are elements of the positive integers inclusive of 0. Now, with this, the next step in order to get to our final thing with the polynomial is quite simple. You see, if it's true for all of the n, then if we just multiply one of these sums by an integer, let's say a, then this whole thing is still going to be an element of the integers multiplied by e. Since multiplying it by an integer just means that you're still going to have an integer at the end. So this a times k here is going to be an integer which is then multiplied by e, which is equal to some integer a multiplied by the sum from r equals 0 up to infinity of r to the power of n divided by r factorial. Now, since this is true for all powers of r, as in r to the power of 0, r to the power of 1, r to the power of 2, and so on, we can finally say that if you just have a bunch of these terms which have r to the power of 0, r to the power of 1, r to the power of 2, and so on up to r to the power of n, then this thing divided by r factorial sum is going to be an element of the positive integer, element of the integers times e. This thing divided by r factorial sum is going to be an element of the integers times e. And then if you add all of them together, integers being added together multiplied by e is going to be some bigger integer multiplied by e. And therefore, finally, from that we can say that if you have any polynomial of r on top, divide by r factorial and you take that thing sum from r equals 0 up to infinity, it is going to be an integer multiple of k. Hence with that we can find a very nice relationship between these kinds of polynomials of r, divide by r factorial sums from r equals 0 up to infinity, and e. We're going to always have an integer multiple of e. So now with that we've proven that this is in fact true. Now let's take a look at the actual coefficients of e that we get when we take the sums from r equals 0 up to infinity of terms of the form r to the power of n divided by r factorial. If we take a look at a few of these terms, for the first term we can consider the sum from r equals 0 up to infinity of r to the power of 0 or 1 divided by r factorial. This is just e. So if we consider the value of n and the coefficient for n equals 0 as in the power of r equals 0, the coefficient is 1. Next, if we consider the sum from r equals 0 up to infinity of r to the power of 1 divided by r factorial, this is also going to be e. So due to this, for n equals 1, the coefficient is still 1. For the next term, as it turns out, if we take the sum from r equals 0 up to infinity of r squared divided by r factorial, this comes out to 2e. So this is equal to 2e, which means that when this is 2, when n is 2, we get a coefficient of 2. Now when you see this, you're probably thinking, oh, it's Fibonacci, right? 1, 1, 2. 1, 1, 2 is very Fibonacci-like. However, the next term is not 3. If you consider the sum from r equals 0 up to infinity of r cubed divided by r factorial, this is in fact equal to 5e, not 3e. So that means for n equals 3, the value that we get here is 5. The coefficient is 5. If we do one more, the next one, the sum from r equals 0 up to infinity of r to the power of 4 divided by r factorial, r to the power of 4 divided by r factorial is equal to 15 times e, which means that for n equals 4, the value is 15. So from this we get the sequence of numbers that initially looks like Fibonacci. It goes 1, 1, 2, but then instead of going 3, it goes 5, 15, and the next number after this happens to be 52, and it goes like that and so on. These numbers are related to something called the Bell numbers, and they can be found using a triangle known as the Bell triangle. So the Bell triangle goes like this. You start out with 1, and then what you do is to imagine a grid where there are rows and columns. You think of this column here as being the very last column, the rightmost column, and then you imagine rows that have columns that stretch out to the left of this very last column. Now, when you have a number in this very last column, what you do is to find in that row the leftmost number, and then that's this number in this case. You go one place to the left of that leftmost number, and then you go to the next row, and then in that row you put this number that you have in the rightmost column of the previous row. So in this case, that number is 1. Then what you're going to do is to start from the left of that row and move rightward, and as you go, when you find an empty space, you put into that empty space the sum of the number above the empty space and the number that is to the left of the empty space. So in this case, the number above it is 1 and the number to the left is 1. When you sum them together, you get 2. Then what you do when you have a number in the rightmost column here is to once again go along that row to the very last number, go to the left of that number, go below that number, and into this place substitute this number. So in this case it's going to substitute 2. Then what you do is starting from the left and going rightward, when you find an empty space, so in this case this is the next empty space, you add into this empty space the sum of the number above the empty space and the number to the left. So that's going to be this number and this number. So it's going to be 1 plus 2, which is going to be 3. So this empty space gets 3. And now we go to the right again. On the right, we can see once again we have an empty space. Into this empty space, we substitute the number that is above it plus the number to the left of it, which is going to be 2 plus 3, which is going to be 5. If we do this one more time, we can see if we take this 5 to the very last point, which is going to be this point, plus 1, divide by below, which is going to be 5 here, and then we continue the process. To this point we get 2 plus 5, so 2 plus 5, which is going to be 7. To this point we get 3 plus 7, which is going to be 10. And to this point we get 5 plus 10, which is going to be 15. Now if we take a look at this last column, we can see the numbers 1, 2, 5 and 15 appear here. These are the numbers in our sequence here except for the first term. So here we get 1, here we get 2, here we get 5, here we get 15. If we do it one more time, we will in fact get 32, and I'll demonstrate that by just doing it. If we take this number here, 15, to the very last position that it should be, which is this position here, we're going to have 15 here. 15 plus 5 is 20, 20 plus 7 is 27, 27 plus 10 is 37, and 37 plus 15 is 52. So therefore it works, and we do get those coefficients. So if you want to quickly find the sum from r equals 0 up to infinity of r to some power of n divided by r factorial, just draw this triangle, and the power of n, if you write that down as the row number, you're going to get the corresponding coefficient of e. So in this case, if I want to find, let's say, r to the power of 6 divided by r factorial sum from r equals 0 up to infinity, then what I need to do is to find the 6th row in this triangle and find its rightmost value. So here we have first row, second row, third row, fourth row, fifth row. So that means this is the 6th row, which means I need to actually compute one more row in order to find this sum. So if I do that really quickly, here we get 52. 52 plus 15 is going to be 67. 67 plus 20 is going to be 87, so 87. 87 plus 27 is going to be 114. 114 plus 37 is going to be 151. 151 and 52 is going to be 203. So 203 is going to be the coefficient of r to the power of 6 divided by r factorial sum from r equals 0 up to infinity. So here we have 203 times e, and that's going to be our answer. So there we go, an interesting little formula that I discovered while making cookies. It's not original, of course. It's very difficult, as I said, to find an original sort of mathematical theorem in this day and age, but you can still think of things like this. So I hope you enjoyed this video. I hope you understood the interesting insight that we can get about the exponential by considering this sum here. I hope you enjoyed. Thank you for watching, and goodbye.